Okay, so good afternoon to all of you. आवाज आ रही है? Okay, so hope every online you are able to see the screen and am I audible? मौसम ठीक है, that's good. We are good to go. Okay, so yesterday in the last class we had discussed triatomic molecules BH2. I think you will go through it again. And so what we had done in this case, we have identified the orbitals of hydrogen. Sorry, uh, we first combined into made group orbitals by combining the 1s orbitals of hydrogen, right? Group 1 and group 2. The combination was done in the same way, CAO approach, linear combination of atomic orbitals, uh, that we did. And it was similar to what we had done for hydrogen molecule, H2 molecule. The difference being that the two hydrogen atoms are now separated by a certain distance, and so doubts can be raised how we are combining them. Okay, so ये एक चीज था, बाकी साइन तो आप समझ रहे थे, तो ये सब चीजें हमने किया लास्ट की क्लास। ठीक है, लेकिन अगर आप ठीक से इलेक्ट्रॉन्स को समझते हैं, इफ यू ट्रूली अंडरस्टैंड द नेचर ऑफ इलेक्ट्रॉन्स, then you will realize that what we are doing is correct. The extent of overlap will be less, no doubt, because the hydrogen atoms are separated by a certain large distance. But there will be some interaction because the amplitude of the wave doesn't go down to zero immediately after that circle. न्यूक्लियस से आप आगे बढ़े, वो सर्कल जो रेड वाला डॉट जहाँ पे दिखा रहा है, रेड सर्कल, वो खत्म हो गया क्या? इलेक्ट्रॉन का वेव खत्म हो गया? नहीं, वो इन्फिनिटी पे जाके जीरो होता है, राइट? सो वहां भी बाकी सब जगह कहीं ना कहीं कुछ ना कुछ इलेक्ट्रॉन डेंसिटी, मतलब दे विल बी वेरी फीबल। 90% यू ड्रॉ दिस सर्कल बेस्ड ऑन द 90% प्रोबेबिलिटी प्रोफाइल, राइट? बट बियॉन्ड रेस्ट ऑफ द 10% इज लाइक समवेयर एल्स अप टू infinity. So you have amplitude of the wave, you have some probability of electron being found there, and so there is a possibility of the overlap, and that's why based on that we group them and make this kind of. So our assumption is not incorrect when we draw this kind of diagram. Okay, so that gives us G1 and G2 orbitals. Okay, so it is the same. So plus plus combination plus sign of the, so this combining with the sign minus sign of the wave function psi. So these are the signs of wave function which is shown through colors, right? And then you identify. So what was the next step? Once you have made group orbitals G1 G2 by combining these two hydrogen atomic orbitals of hydrogen, you identify what are the suitable orbital in beryllium that can overlap with each of these. So if you observe carefully, you will find that the 2s in beryllium and 2pz, the z orbital, can combine with the G2 set. So G2 goes along with 2s, so 2p, and G1 goes along with 2s of beryllium. So now once you identified that, then you can think of having both kind of interaction, constructive as well as destructive interference, and so you can write in phase, so you can think of outer phase combination, and you can write another equation. Remember, you are swapping this coefficient a b here. When it is minus g1, the coefficient is interchange, है ना? ये बहुत सिंपल है, जो हम लोग पहले भी बार बार डिस्कस कर चुके हैं। जब ऑर्बिटल्स की एनर्जी लेवल सेम नहीं है, तो कोफिशिएंट्स, दिस statistical weight which is shown by these coefficients a and b will have which represent the different contribution. Okay, so one which is in a higher energy will contribute more, and so and uh, will contribute more to the non-bonding, and the other orbital, which is lower in energy, will contribute more to the bonding. So that's why you have this A and B coefficient, and in the second one, in the outer phase combination, that these coefficients are interchanged. Okay, so then we simply expand this G1, which is HA due to the combination of HAHB, and similarly here also. So you get this kind of pattern. So you got the 2s combining with G1. You got both in phase, considering the in phase and outer phase combination. You got now 1 sigma psi 1 sigma psi sigma 1 star. So both bonding and anti-bonding orbital for the molecule, that is settled. Now you can move to the next, that is the combining this particular thing with the p orbital of beryllium. ठीक है, तो ये जब आप करते हैं नेक्स्ट पार्ट में, तो G2 is going to combine with 2pz. Again you will start writing the wave function for 2p, wave function for G2, and the statistical coefficient C, D, like that. And these coefficient will be again interchanged when you are taking the outer phase combination. So now you can see it is D, it is C when you are writing. So when we are writing minus sign, we mean that the G2 जो यहाँ पे पॉजिटिव है नेगेटिव है वो इंटरचेंज हो जाएगा, प्लस माइनस. सो रेड एंड ब्लू कलर्स विल बी इंटरचेंज्ड, and you will have this thing. Okay, so this ABCD that we have written are the statistical coefficients which tell you about the relative contribution each orbital is making is towards the formation of the orbitals. So when you look at the energy level diagrams, which is molecular orbital diagram for this, it's easy to understand now. This first orbital that we considered was due to the constructive interference of hydrogen 1s here, and the beryllium 2s, right? And the counterpart of destructive interference was the sigma 1 star, which is here when we consider minus G1. So plus plus, these both of them, the sign of hydrogen 1s is interchanged. और आपका due to the destructive interference you have nodes appearing on this part. So these are the nodes which were earlier not there. Similarly, now go for the other thing. So this whole envelope of red, envelope of blue, what does this represent? The p orbital, which is having plus sign, overlaps with the plus sign of hydrogen atom, and this is hydrogen 1s orbital. And in the similar way, the other side of beryllium, you have negative p orbital has a negative sign of the wave function, which overlaps with hydrogen 1s, which is with a negative sign. So that is the overall. So on both sides you have electron density, and there is a node that was originally present in p atomic orbital as well. There is nothing, you are not adding any node further by making this orbital. इसमें पहले से ही था, बेरिलियम एटम में pz orbital में था ही एक नोड पहले से. Now when you come, so this is your sigma 2, then you are आउटर फेस कॉम्बिनेशन, उसको उलट दो, दोनों हाइट माइनस G2 आपने लिखा था वहां पे, तो जो प्लस माइनस यहाँ पे था रेड और ब्लू, उल्टा कर दो ब्लू एंड रेड. सो दैट्स हाउ यू गेट इट. सो डिस्ट्रक्टिव इंटरफेरेंस यहाँ पे ये डिस्ट्रक्टिव इंटरफेरेंस से दो नोड और आगे. So how, so you are having a number of nodes if you are looking at it. So look at the number of nodes then you had 0 1 2 3 है ना, तीनों में दिख रहा है. So we have arranged them well. So this is how the ordering of energy would look like this. Number of node आ गया, मतलब दो न्यूक्लियाई के बीच में इलेक्ट्रॉन डेंसिटी 0 हो जा रही है कहीं पर, on the line joining the two nuclei. So that is not a happy situation, and so that will cause an increase in energy. Repulsion between the two nuclei will increase, so energy will increase. जो आपने फंडामेंटल अगर समझा है, जो अब तक मैंने बताया है, तो उसके बेसिस पे आप ऐसे जितने पॉइंट्स नोट्स बढ़ रहे हैं उतना ही आपका वो बढ़ेगा एनर्जी. दैट्स नॉट डिफिकल्ट टू इमेजिन. और बाकी के जो दो ऑर्बिटल है, एक पी ऑर्बिटल जो परपेंडिकुलर टू द प्लेन ऑफ द बोर्ड है, वो बाहर निकल रहा है, ब्लू रेड उधर, और एक ऐसे परपेंडिकुलर इसमें. सो इन दोनों का कोई काउंटर पार्ट ही नहीं है. देयर इज नो काउंटर पार्ट टू ओवरलैप फ्रॉम द हाइड्रोजन एटम्स side. From the hydrogen atom side, there is no such orbital which can overlap with these two, so they remain, uh, the energy remains unchanged. That's the equivalent of saying that they are non-bonding. So this is the same diagram in a black and white picture with the signs instead of colors. If you have to use sign, then plus, remember how you represent it, plus minus, so that how you are creating these lobes of the molecular orbital, that you identify this. And so this is how you had the same as this one, this second, then third and fourth number of nodes, 1 2 3, 0 1 2 3. Okay, so these are the 1s orbitals, hydrogen 1. So you also understand that as compared to hydrogen, so in this scheme, just a moment, let me take out. So when we are working out this combination, you should also realize one thing, that when we were having in H2 molecule, you had two hydrogen atoms overlapping. This was HA, this was HB, and this is the sign of wave function that you. Now you have this is slightly away from each other with beryllium, and then so this is what we have done. Fundamentally, this is what we have done. In this is having plus sign, and then we are combining and discussing the whole thing. So obviously here the overlap very good. Good overlap here, because you have greater electron density in this part. There will be very feeble overlap, because why we are doing this, because if we understand this part with psi radial wave function, the wave function decays to 0 only at infinity. So it is definitely having a higher amplitude over here, so interaction, good overlap, and good interaction is happening. Here there will be very less interaction, but there will be a interaction will be there. Okay, because so the amplitude becomes 0 only at 0 only at infinity. And so the circle is not a restriction on that. जो हम बाउंड्री दिखाते हैं सर्कल का ड्रॉ करके, ये ऐसा नहीं है कि इलेक्ट्रॉन डेंसिटी उसके बाहर नहीं है. उस 1s इलेक्ट्रॉन की इलेक्ट्रॉन डेंसिटी आपको इन्फिनिटी तक होगी, थोड़ी थोड़ी, लेकिन मेजर इलेक्ट्रॉन डेंसिटी उस सर्कल के अंदर है, जो 90% इलेक्ट्रॉन कहते हैं, 80 to 90% like that. So there is some interaction when they are separated by certain little further, and that is what we are making G1 and G2. ये चीज समझने वाली बात है, ठीक है. इसीलिए हम इसको ये सब sorry. Okay, so these are different views. जैसे भी आपको समझ में आया, इसलिए अलग अलग पिक्चर मैंने आपको सब ड्रॉ करके दे दिया है। सारे ऐसे कंबाइन करके देख रहे हैं, यहाँ पे आप देख रहे हैं। सो दिस इज व्हाट वी वर ड्राइंग, दैट कंबाइनिंग ब्लू ब्लू टुगेदर। एक यहाँ पे इन दोनों को करेंगे, एक बड़ा सा लोब, ऐसे आपको कंस्ट्रक्ट करते जाना है। यहाँ पे आपको, so you are getting this destructive interferences here, like this you consider, and then these two are the p orbitals. So ABCD तो वो रिलेटिव कंट्रीब्यूशन बता रहा था, रिप्रेजेंट्स। ABCD क्या था? ABCD were the coefficients which were telling you the differing contribution of atomic orbitals, which in making of which goes into the making of bonding or anti-bonding molecular orbitals. And so we have seen that in all these pictures, the electrons, the electron density, electron is delocalized over the three atoms, which is a consequence of the simple the way we have considered combined these atoms. So it is a simple general result of molecular. So there is no additional resonance or other term that we have to import from somewhere else. There's a natural when we treat it in this manner, the delocalization comes automatically when you have more than two atoms. मोर देन टू एटम्स, ये डीलोकलाइजेशन अपने आप आ जा रहा है। आप देख रहे हैं पिक्चर्स के थ्रू, जैसे ही आप वेव नेचर को कंसिडर करके ओवरलैप इस तरह से करते हैं कि 2 से 3 ऑर्बिटल कंबाइन कर रहे हैं, द electron density is spread over a large area, so that is throughout the all the three atoms have the electron density. So this when you put an electron in these two orbitals, sorry, in this orbital, that means it will be under the influence of attractive force of all these three nuclei. ठीक है, ऐसा नहीं कि दो के बीच में जो कोलाइड है, ऐसा व्यू है। और इसलिए so this is something that automatically comes in to picture when you have when you do this for this. Okay, so let's another point was that why we didn't consider 1s orbital in beryllium. It is a simple reason, because if you compare the energy of 1s of beryllium and 1s of hydrogen, they are separated by huge difference. There is a huge difference in energy. So one of the basic criteria for combining these orbitals is that they must be closer to each other in terms of energy. Then overlap is good. So we found 2s orbital to be better in terms of energy, better matching of energy with the 1s of hydrogen. So that's why we have considered only 2s when discussing these things. Now this is we move to the slightly different things in this triatomic molecules, like the case of water, H2O. Why water is bent and why this BH2 is linear. So how can we understand that through this in the framework of MOT? So there is something called Walsh diagrams, which tells you about the relative energy of the orbitals, molecular orbitals. So and how it will change when you change the geometry. So linear से bend करने में कैसे वो सारे ऑर्बिटल्स जो हम देख रहे थे linear फ्रेम के लिए था, linear से अगर हम उसको bent फ्रेम में कर दें तो क्या कैसे how the energies will change. So उसको लेकर के सारा अगर हम डिस्कशन करते हैं, then we will realize that we will understand why water is bent or why BH2 is linear. So the simple thing that is considered, uh, so you have to look at the HOMO and LUMO, that lowest unoccupied molecular orbital, highest occupied, sorry, energy of the highest occupied molecular orbital is important to consider. So it is the consideration of these two things that is crucial in determining what geometry is adopted by the triatomic molecule in this particular case. So Wald's prediction is based on that it says that the molecule will adopt a structure that provides stability that gives stability means you are giving having lower energy, so which gives you lower energy for the HOMO, which conformation, whether it's a 90-degree geometry, 180-degree angle, which one is giving you best uh, lowering in energy, so that will be the most stable one and it will exist in that form. So if the highest occupied orbital remains unchanged in energy when the structure is changed, then we'll go for the next closest one. So let me just okay, we have just considered the, so this is one of the ways of representing Walsh diagram, 180-degree on this side, 90-degree. But let me go back to the, sorry, I'm going to the next. Yeah, this is a picture that is better to understand because we have just discussed the BES2. So this side is the linear, लीनियर वाला आपका इधर है, ये सारा ऑर्बिटल अभी हमने देखा, जस्ट अभी डिस्कस किया है, ठीक है, इधर हमने प्लॉट किया। राइट हैंड साइड में जो पैनल है, अब उसी ऑर्बिटल को, वो जो तीन एटम्स का अरेंजमेंट है, we are changing that arrangement, making it bent. Okay, so from linear frame to a bent one, when you try to do that, what happens, how the energies will change, so that is being discussed through this diagram. That is what is being conveyed through this diagram. So look at the first one. We have, like in case of beryllium, you had beryllium at the center, 2s hydrogen atom in a linear frame. अब उसको आपने थोड़ा सा बेंड कर दिया तो क्या होगा, दिस वन, सो अगर हम इसको बेंड करते हैं स्ट्रेट, सो यू हैव, so these two hydrogen atoms, the valence orbitals are coming closer to each other. तो अब जितना पहले ओवरलैप हो रहा था उससे ज्यादा बेटर ओवरलैप. So because of the better overlap between the hydrogen valence orbitals, the energy will be lowered, and that's why it is shown like this. The second picture is about this, that pz orbital overlapping with, so okay, online वालों के लिए दिक्कत हो जाएगा, इसी में बताते हैं. So यहाँ पे था, so this is your this is for the linear, ये दोनों क्या है फ्रेम में, what is this, this is the for the linear frame. अरे जाओ, ये linear और ये bent, ठीक है. So how the, when the same set of orbitals which we have just considered in the formation of BH2 molecule, how does the energy will change, how does the energy change when they are bent, linear से थोड़ा bend करें तो क्या होता है, वो कंसिडर करने के लिए ये दिखाया गया है. So yeah, the first one what we found, that when you are bending the things, थोड़ा सा ये इधर चला गया है, हाँ, so when you bend, so the two hydrogen atoms, so suppose AHA, that is we are writing here, so this, look at this A could be बेरिलियम और ऑक्सीजन, ठीक है, बाकी मॉलिक्यूल का चीज़ें सारा चीज़ हमारा डिस्कस हो जाएगा, चाहे BH2 हो, दोनों ही केस में हाइड्रोजन कॉमन है, द सेंट्रल एटम इज चेंजिंग, ठीक है. तो पहले हम ऐसे समझ लें, वाई BH2 इज लीनियर, व्हाट विल हैपन टू BH2 इफ इट इज बेंड. तो पहले हम इसको कंसिडर करते हैं, तो BH2 में हमारा दो ही ऑर्बिटल, हाउ मेनी इलेक्ट्रॉन्स आर देयर इन BH2, बेरिलियम यू हैव 2 and the 2 electrons from the hydrogen, so you have 4 atoms, 4 electrons. So this is in linear frame, so 2 electrons goes here, 2 electrons goes here, and this is your, so this is your highest occupied HOMO in BeH2. This is what we have already seen. So two electrons will be here in this orbital. Okay, this particular orbital is, this is your HOMO, expression of HOMO. यहाँ पे दो इलेक्ट्रॉन होंगे, दो इलेक्ट्रॉन, 2 plus 2, 4 electrons you have accounted for. Now when you are looking at this picture, you clearly see that in the uh, first orbit, this orbitals, this one, the energy decreases. Energy decreases. Why? Because the two hydrogen atoms are brought closer. आप थ्री डायमेंशनल फ्रेम में डिस्टेंस देखिए, ये एक स्ट्रेट लाइन है, इसको आप बेंड करेंगे तो ये जो दो कोण, दो डॉट है, ये तो पास आएंगे ना, दोनों का न्यूक्लियस पास आएगा, दोनों का इलेक्ट्रॉन क्लाउड पास आएगा, तो दैट बेटर होगा, है ना. So इसलिए because they are coming closer, you can see in this picture they are the two hydrogen atoms are brought closer. The overlap between the 1s orbital जो हमने G1 के consideration में किया है, G1 group orbitals, वो वहाँ पे वो overlap अच्छा होगा, वो so this is getting more stabilized in that. So the energy becomes lower because these two hydrogen atoms get closer, which gives better overlap. And this is constructive interference, right? So better overlap, constructive interference. So lowering of energy. So this is how you are interpreting these things. That's why we are showing this. ठीक है. और दूसरे केस में क्या है, ऊपर वाले में, उसके बाद जो ये हमारा इस वाले ऑर्बिटल के केस में था, ठीक है. इसके केस में क्या हुआ, हाईएस्ट ऑक्युपाइड मॉलिक्यूलर ऑर्बिटल जो कि क्रूशियल है, when we, let me make space for that. Now we move to the HOMO. What happens to the HOMO in BeH2? In case of BeH2, when we are considering एक मिनट, मेरे पास zoomed in picture है, ये ज़्यादा बेटर होगा. हाँ, so we are just zooming into the this thing. So we have, this is the HOMO, highest occupied molecular orbital in BeH2 for BeH2. इसमें क्या हो रहा है, BeH2 में अब यहाँ पे जो इसके एनर्जी कैसे चेंज हो रही है, द टू हाइड्रोजन एटम्स, एक का प्लस साइन है, दूसरे का माइनस है, राइट. हमने पहले वाली सिचुएशन में डिस्कस किया कि जो दोनों हाइड्रोजन एटम्स पास आ रहे हैं, ओवरलैप अच्छा हो रहा है, कंस्ट्रक्टिव इंटरफेरेंस इज वेरी गुड, so there is a greater increase in the amplitude of the wave, greater increase in the electron density between two atoms, so that is a happy situation, lower. The same thing applies to destructive interference, though उतना ही electron density घट जाएगा, so so the energy is increased. So because it increases, the two signs are different. So they are now, the two hydrogen atoms are brought closer to each other, each one having different sign of the wave function, which increases their extent of destructive interference. ठीक है, उसके बीच में destructive interference बढ़ गया, ठीक है, तो एनर्जी बढ़ेगी. सेकेंड, अनदर थिंग यू कैन, बहुत ध्यान से देखिए, यहाँ पे जो ओवरलैप है और यहाँ पे जो ओवरलैप है पी के साथ, वो भी कम हो गया. सो बिकॉज ऑफ दीज टू रीजन्स, अगर सिर्फ एक रीजन होता कि कंस्ट्रक्टिव, जितना इधर कंस्ट्रक्टिव हो रहा है उधर डिस्ट्रक्टिव हो रहा है, तो दोनों का, देयर शुड नॉट बी एनी चेंज इन द ओवरऑल थिंग. But the second factor, when you look at the how the p orbital, pz orbital overlaps with hydrogen in the bent form, then you realize that there is further the overlap area has decreased. When we consider, when you are bending the molecule, the 1s orbital has a poor overlap with the pz orbital, and that is the decisive factor. अब ये energy, so the increase in energy of this HOMO is much more as compared to the decrease in energy for the this particular. And so if the BES2 adopts this bent geometry, its energy would be higher, it will be unstable. If BES2 adopts this geometry, it will be having lower energy, and that's a happy situation. So that's why BES2 is bent. Oh, sorry, BES2 is linear. Now we apply the same argument to the water, case of water, with the same diagram. In case of water, you have how many electrons to be put in these orbitals? 6 plus 2, 8. H2O, you have 8 valence electrons. So 2 इलेक्ट्रॉन यहाँ पे जाएगा, ठीक है, 8 electrons. Case of water. Now in the case of water, so पहला दो तो हमने डिस्कस कर लिया ऑर्बिटल्स का कैसे चेंज हो रहा है. In the case of water, as discussed in the Walsh statement, opening statement of the Walsh rule, he said that if look at the HOMO, highest occupied orbital is this, the p orbital, which is perpendicular to the thing. Suppose if water is, but this particular orbital, जो non-bonding है, it is not having any change when the geometry is, you change the geometry from linear to bent. So we look for the energy of the next highest occupied orbital, molecular orbital. So that is this one. तो ये जो जब बेंड करते हैं, तो जो पहले this was initially non-bonding in linear becomes participates in bonding because now the overlap is possible with the, when it is moving, bending like this, then these two hydrogen atoms, hydrogen 1s orbitals are coming in contact with this lobe. They are coming closer, and now the geometry is such that this overlap can happen. So this participates in bonding. जो नॉन बॉन्डिंग पहले था वो बेंट ज्योमेट्री में अब बॉन्डिंग हो गया है. तो एनर्जी ऑफ द ऑर्बिटल इज will go down because now you have a constructive interference in this side, and so ऊपर वाला जो हाईएस्ट ऑक्युपाइड ऑर्बिटल उसका कोई चेंज नहीं है, लीनियर से बेंट हो जाए उसको कोई फर्क नहीं पड़ता. लेकिन ये जो दूसरा ऑर्बिटल है जो पी एक्स लिखा हुआ है यहाँ पे, हाँ पी एक्स है, वो बेंड करने के साथ इसका इट हैज़ अ बेटर ओवरलैप विद द 1s orbitals of hydrogen, and so the energy of this is lowered. This is so because of this the energy, this is lower energy in the bent form, and that's why water is bent. Okay, so जो अभी let's go back to the original statement. So Walsh's statement was stated molecule will adopt a geometry that best provides stability to the highest occupied orbital. अगर if the HOMO is not affected, whether it is you change the geometry, then you look for the next closest occupied molecular orbital. So in the case of water, we are applying that second. ये वाला चीज apply किया हमने. We applied this thing. So overall, जो वाटर में जो ऊपर वाला था फील्ड ऑर्बिटल उसका एनर्जी अफेक्टेड नहीं हो रहा है, लीनियर करो बेंड करो, वो लोन पेयर है, उसका कोई फर्क नहीं पड़ रहा है। लेकिन जो हमने लास्ट में अभी देखा यहाँ पे, जो नेक्स्ट क्लोजेस्ट है फील्ड ऑर्बिटल, उसका एनर्जी अफेक्टेड हो रहा है और वो कम हो रहा है, बेंड फॉर्म में कम हो रहा है, लीनियर में ज़्यादा है। So it will adopt geometry which is bent. So this is what we can the based on Walsh diagram how we interpret these things. And so some of these terms that we are using comes is coming from the group theory. So अभी ये जो डायग्राम में लिखा हुआ ना A1 B1, ये आपको अभी ग्रुप थ्योरी बताएंगे, उसमें ग्रुप थ्योरी पे हमें जल्दी जाना पड़ेगा, अदरवाइज लेट, okay, we'll have to spend a lot of time. So, so because of this reason, so BEH2 why it is bent, what we have just discussed, the same thing is stated over here. So you have overlap of the functions. So overlap wave function that is positive everywhere. This, this, right? So overlap as a two 1s orbitals wave functions are now. So this is the first thing. यही मैं बार बार आपको भी समझा रहा था कि वो जीरो नहीं होता है। आप सर always show by drawing a finite circle that circle is not their limit, कि यहाँ पे आके इलेक्ट्रॉन खत्म हो गया, लिखते के बाद इलेक्ट्रॉन जीरो है, तो आप बेसिक अंडरस्टैंड जो है वो नहीं समझ रहे हैं। So although you represent it by drawing a circle, the electron density is not zero beyond that point. It is zero only at infinity. So that's the reason why we have. Okay, so the first one, why it is going down in energies, then second, why it is rising in energy. So that, and then further, because there was greater destructive interference, and then second point, that the overlap with the two pz orbitals when we it becomes less efficient in bent condition, इसीलिए इसमें linear geometry prefer किया BEH2 के केस पे. So we have a linear geometry for BEH2. When we apply the same argument to water, we have 8 electrons to be put gradually in these orbitals. ठीक है? And so we look at the so this is the orbitals to be considered, highest occupied orbital in, okay, so this was your homo, highest occupied molecular orbital for water in case of water, and which remains unchanged. So we'll look for the energy of this one, which is due to the px orbital, which was not having any interaction with the 1s, but when it is 1s orbital of the hydrogen, when the structure is bent, then they are having overlap, so energy decreases. So something that was non-bonding initially in linear geometry, non-bonding in linear becomes bonding in bent. Overlap becomes better, and so this is the stabilizing factor. The energy is lowered and S2 adopts bent geometry. So once you, so it is the same set of things, G1, G2 group orbitals that we consider here. So अब आप जैसे BH2 में जो BH2 के केस में जो हम ग्रुप वन ऑर्बिटल्स दिखा रहे थे G1, G2, उसके बीच का सेपरेशन बहुत कम होगा। यहाँ पे थोड़ा सा बेटर इंटरेक्शन है तो सेपरेशन ज़्यादा होगा। जब हमने कहा कि बेंट फॉर्म में वो पास आ गए, तो नाउ ओवरलैप इज बेटर, सो दिस रिलेटिवली थोड़ा सा स्पेसिंग आप दिखाते हैं, ठीक है। एंड so the situation is similar to what we have. So this energy of G1 is intermediate between the 2py and 2s orbitals, so it can overlap with both of them. दोनों के साथ ओवरलैप, टू पी वाई नहीं, सॉरी। सो बहुत अच्छा कलर कोडिंग, डायग्राम को ध्यान से देखिए, कलर कोडिंग बहुत अच्छे से किया गया है। आप देखिए, जो सिमिलर सिमिट्री और एनर्जी के टर्म्स में कंबाइन हो सकते हैं, उनको ब्लू दिखाया गया है, ब्लू से यहाँ पे देख रहे हैं। सो पी जेड ऑर्बिटल, टू पी जेड, इधर पिक्चर भी है आपके साथ में, बेंट ज्योमेट्री भी। तो यहाँ पी जेड ऑर्बिटल कंबाइनिंग विथ दिस G1 पी जेड, ये वाला, ठीक है। यहाँ पे 2s ऑर्बिटल, यहाँ पे हम इसको देख रहे हैं ऑक्सीजन पे। सो दिस इज योर ऑक्सीजन and G1, G2, the group orbitals of hydrogen. So based on symmetry consideration, we find that this orbital can combine with both the pz and 2s. And so जैसे हमने CO के केस में देखा था, if we combine three such orbitals, we'll get one bonding, anti-bonding and one non-bonding. Similar situation happens here. यहाँ पे जो है वो आप देख रहे हैं, ये बॉन्डिंग, एंटी बॉन्डिंग और ये नॉन बॉन्डिंग सिचुएशन में हो जाता है। सो एंड रेस्ट ऑफ द थिंग्स, सो दिस G2 इज कंबाइनिंग विथ PY बेंट कंडीशन में, इट इज पॉसिबल दे विल बी ओवरलैप। सो ये सारा कॉम्बिनेशन वर्कआउट किया गया है, ओके। And so this is the filling of orbital. So this is the non-bonding. Sorry, this is the non-bonding situation for the PY. PZ is now having overlap. Yeah, यहाँ पे हाँ PZ. So energy, overall energy is slightly less. So so this is the same expression that we have just discussed. So this labeling A and B, this is coming from the group theory, which we will discuss later on. After learning group theory, we can again review this to have a better understanding. बाद में करेंगे. So that's all for triatomic molecules. We are not so sigma star mixtures, small oxygen 2pz atomic orbitals energy 2a1. So all these things are described, which we have just discussed. Okay, we can go through it. So highest occupied orbital is non-bonding, localized on oxygen. Next lowest 2a1 can be thought of as non-bonding, as it is a slope. So this is what we have just discussed in this. ठीक है. So ये this brings to the so first, second, the highest we have just seen in the two pictures, and so the Walsh diagram, there is one more point that is important here. It is accurate only for molecules in which there is large separation between NS and NP energy levels of central atom. If it is small, then it may not be that much effective. The Walsh diagram is so this is a limitation of that. Okay, so this is particularly observed in case of fluorides, MF2 type, strontium fluoride, barium fluoride. This situation arises where it is found to be ineffective in determining so they are also triatomic molecules, but the prediction by Walsh diagram is not good. Okay, so in the same manner we can extend the concept to four atoms or this. So but we are not going for the time being, we are not going into the details of the four atoms, because yeah. So you try to understand up to this. Oops, sorry, where is that?